Okay, welcome to Math 310, Introduction to Modern Algebra. So this is the last of the lectures that will be on material that will be on the final exam. So anything we do after that is going to just be, fun, special topics. If there are things you would like to hear, let me know, and I'm happy to incorporate that. But in terms of what you need to learn for the exam, nothing beyond today will be on it. Okay, so what I want to do is just go over some of the stuff we've seen a little bit in the last lecture or two, and then just put in some of the details. So G, as always, is going to be a group. I think we've talked about the center of G a couple of times. So the center of G, denoted by Z, is the set of all elements of G that commute with every element of G. So G prime equals G prime G for every G prime. Is it possible for the center to be empty? Could you have a group where there's no element that commutes with everything else? Or must there always be at least one element in the center? The identity, right? And so, in fact, if you look at remark 6.24, it says, prove that it's a subgroup. Well, if it's a subgroup, we really want the subgroup to have at least one element. And the element we know has to be in it, if it's a subgroup, is the identity. So let's quickly prove this. So proof. So what are the four properties we have to show if we want to show that the center is a subgroup of G? What do we have to show? What four things? We just mentioned the identity. So you have to show that E is in the center. That's not too bad because the identity commutes with everything. What else do we have to show? What are the properties to be a subgroup? Closure. So that's one of the harder ones. So if we have G1, G2 in the center, and G is anything in G, then we have to show G1, G2 is in the center. So G1, G2 is G1, is G, G1, G2 is G1, G, G2, just doing associativity really slowly, is G1, G, G2 is G1, G2, G is G1, G2, G. So that does show that you could be any element in G, then just using associativity up the wazoo, we slowly move things over one at a time. You first move G1, then you move G2. Okay, what else do we have to do? We have two more properties. We did identity, we did closure. What else do we got? Associativity, and it inherits that. And what's the last one? Inverses. So I'll leave that for you. So you have to show that if G is in the center, so is G inverse. So show if G is in the center, so is G inverse. Okay. So the center is going to be an extremely nice subgroup of G. If life was really good, how many elements would be in the center? So all of them, right? That would be wonderful. And then what kind of group would we have? A billion. So the center is basically telling you in some sense how far away you are from being a billion. Okay, let P be a prime number and G be a finite group with P to the n elements for some n greater than or equal to 1. So it's always interesting to ask, would these theorems work if the order was not a prime power? Is this an assumption to make the proof easier or not? Assume the center is not the identity element. So how many elements must be in the center? What can you tell me about that number? If I'm telling you the center is not the identity element, what do you know about the size of the center? Yes, it's more than one. So we know that there has to be at least one other element in the center that is not the identity. Or did I misread this? Oh, I'm sorry. I misread the conclusion. Sorry. Let P be a prime, let G be a finite group with P to the n elements for some n greater than equal 1. Then the center is more than the identity. Sorry. So there's at least one element that is not the identity. As soon as you know that there's at least two elements, I claim that you can tell me something more about the size of the center. You can do better than it's at least two elements. Because the cardinality of G is P to the n. So what can you tell me about the size of the center? So we've used this theorem numerous times to talk about sizes.
The order of the subgroup needs to divide the order.
The order of the subgroup needs to divide the order of the group. And so if the group has size P to the n, and the center is more than the identity, it has to have cardinality more than one. So what's the smallest the center could be? P. It has to have at least P elements now. So this is one of the really nice results. You can prove if it's more than just the identity, it has to be, in some sense, a lot. So proof. Any thoughts about how we should prove this? So this is in the book, and it's a really nice formula that we've proved, but haven't really used yet. So let's see if I can find. So we started talking about orbits, and that the number of elements in the orbit is equal to the number of elements in G divided by the size of the stabilizer. And then we had the orbit stabilizer counting theorem. The number of elements in X is equal to the sum of the sizes of the orbits, because each orbit is distinct from all others. So this was very similar to our cosets. Either two cosets were the same or they had no elements in common. Two orbits are either the same or they have nothing in common. So if I want to count how many elements there are in X, I just have to count how many elements are in each orbit, each distinct orbit. And each distinct orbit, the number of elements there is the size of the group divided by the size of the stabilizer. So this is a very useful theorem. Okay. So we have the size of X is equal to the sum, K goes from, say, 1 to n, of the size of G xk, I'm sorry, the size of G, divided by the size of the stabilizer of xk. And this is where we have to be somewhat clever. I'm giving you the group G. What have I not given you? If I want to use this formula, what else do I have to give you? Well, close, but not quite this X, right? I have to tell you what X is. There's a lot of different choices for X. This is where computers are going to beat the crap out of us. They will just go through a huge number of possibilities. And it doesn't matter if they're a little bit slow, they can do so many possibilities, they will just find, here's the X that works. We have to be a little bit more clever. And we have to try to figure out what is the right X to use. So one of my students just gave me the highest praise. I was the first person other than his parents that he called. He finally got the job. All the paperwork finally cleared. That I was absolutely right when I taught him in multivariable calculus. He was never going to use any of the content ever again in his life. But the thought process, how to attack problems, absolutely essential, and that's made a huge difference in his career. You are not going to be using theorem 6.25 almost surely in the rest of your life. Same thing with the CELO theorems later on, you're not going to be using them. What I really want to emphasize is the thought process of how you attack problems like this. If you are thinking of going to math grad school, please send me another email about this, and I will talk to you about what you need to do to make sure that you're prepared for something like that. But most of you, you're not going to be using this stuff, so I really want to talk about the thought process. We have to choose X. Any thoughts on what would be a good choice for X? So we need to find a set that the group G acts on. Any thoughts on a set that G acts on? There's always one thing that works. Itself, right? So let's, take X equals G. But it's not enough to just choose the set. I also have to choose how G acts on the set, right? How should G act on itself? Let's define G dot X to be G inverse XG, and this is called conjugation. This turns out to be a really natural thing to look at. Why? If G inverse XG equals X, that implies XG equals GX. Multiply by G on the left. So you can see that maybe this is going to be related to which elements commute with X. If G commutes with X, then G inverse XG is just X. So if X commutes with G, then G inverse XG is just X. So what is the stabilizer of X going to be? So if I give you an X, what would the stabilizer represent?
GX equals X.
Okay, is all G which commute with X? Right? Because if you're in the stabilizer, G inverse XG equals X. So the stabilizer is all things that commute with X. Okay. So now let's look at the formula. What do we know about the size of X? What does that equal? Which is? So what's the size of G for this problem? I'm sorry? Not necessarily prime. P to the n. And then we know the size of G equals P to the n. And the size of each stabilizer, what are the possible values for the sizes of each stabilizer?
P squared.
Almost. So P squared all the way up to P to the n. What are you missing? 1. It's possible that the stabilizer could be 1. That maybe the only thing that stabilizes, given X is just 1. So we want to try to get a contradiction to the center just being the identity. Let's get rid of a blank page. So when we're looking at the cardinality of G divided by the cardinality of the stabilizer, what are the possible values for the cardinality of G divided by the cardinality of the stabilizer? What could those be?
1 to n, like 1, 2, 3, 2.
Almost. If the stabilizer has size 1, what would that ratio be? So we've got the cardinality of G is p to the n. If the cardinality of the stabilizer is 1, what would that ratio be? P to the n. If the stabilizer has size p, what would the ratio be? P to the n minus 1. And goes all the way down to 1. So notice all of those numbers are divisible by p except for 1. Okay. And so we have this formula. And so when we look at our formula, we have the cardinality of x is equal to the sum. K goes from, oh, wait a minute. I shouldn't use n over here because we're using m, and it's the size. We'll do nm. So K goes from 1 to m of the cardinality of G divided by the cardinality of the stabilizer of xk. And so we get P to the n is equal to a sum. K goes from 1 to m, and it's going to be something of the form P to the n minus rk, where rk is in n minus 1 all the way down to 0. Okay. We know this side, the left, is a multiple of p. So this must be a multiple of p. Is there any danger in one of those terms not being a multiple of p? So each term is going to be p to the n minus some rk. We showed that the stabilizer is either going to be of size 1, p squared up to p to the n. So this ratio is going to be either p to the n minus 1, all the way down to 1. What's the only time that ratio is not a multiple of p?
1.
1. And so what would it mean not to be multiple of p? So it's a term, p to the n minus rk, which would be the size of G divided by the size of the stabilizer of xk, is not a multiple of p only when the size of the stabilizer equals p to the n. Is there any element that has a stabilizer of size p to the n? Can you think of any element? As soon as I ask you, can you think of any element, what element should you be immediately thinking about? The identity. I'm not even listening to what else you're saying. You just said, can I think of an element? Identity. It's the only thing that you can try. So note, what is the stabilizer of the identity? This is the set of all G such that G inverse E G equals E. That's everything, right? Everything, because G inverse identity G is just G. Is everybody comfortable that this is the entire group G? That everything stabilizes the identity? So now look at what's going on in our equation. The left-hand side is a multiple of P. we know there's at least one term on the right-hand side that's not a multiple of P. So at least one term on the right-hand side is not a multiple of P. Is it possible that there's only one term on the right-hand side that's not a multiple of P? Well, the left-hand side's a multiple of P. The right-hand side has to be a multiple of P. Every term on the right-hand side is a multiple of P unless RK equals N. And we know there's at least one element where RK equals N. When we look at the stabilizer of the identity, we know we get one. Is it possible that that's the only element whose stabilizer has size P to the N? If that was the only element where RK equals N, if that was the only time, the stabilizer had size P to the N, then every other term on the right, but that one summoned, would be a multiple of P. So there must be at least one other element whose stabilizer has size P to the N. So must be at least one more element with stabilizer of size P to the N. Else the right-hand side is a multiple of P plus 1. And that contradicts left. P divides left-hand side. So we know there has to be at least one more element whose stabilizer has size P to the N. Well, if your group has P to the N elements and your stabilizer has size P to the N, what does that mean your stabilizer is? So what must the stabilizer be? If the stabilizer is of size P to the N and the group is of size P to the N, the group, right? So there exists some X such that the stabilizer is all of G, which means X commutes with all of G, so X is in the center. And X is not E. So there has to be at least one more element. Unless the prime is 2, there has to be more than just one more element. If the prime is 17, then that would give me the right-hand side is a multiple of P plus 2, if that was the only other element. So you can push this forward, or you can use Lagrange to know that we have to have subgroups of size dividing the size of the group. The center has to be more than the identity. So a really good question is, what if I gave you a group, let's say, of size 2 times 3 squared? Must that have a center that's more than just the identity? Or is there something special when I have just the prime P and no other prime factors of the size of the group? You can see that we are crucially using some divisibility properties. If the group was more than just a power of P, then I start to have more things that can come into play. Maybe certain linear combinations could then give me pushes into everything working out. And so it's not clear that this proof would generalize if your group was not just a prime power in terms of size. So this, I hope, gives you a sense of how you do problems like this. Okay. you first have to figure out what do you want to apply your group to? What do you want to choose X to be? And it's like the baby is crying, it's like doing your integration techniques. When you're first learning, it's kind of daunting how to figure out which to try. But after a while, you start to realize there are better ways to do things. I'll risk this. So integrating over sphere of radius r, x squared plus y squared. I'll do it as dv. Do people remember their spherical coordinates and integrations for multivariable calculus? So I always have trouble when I teach this because I learned spherical coordinates first in my physics classes, and then I learned in my math classes. And the physicists and the mathematicians have slightly different notation as to which is the angle. So if you've learned it from a math class, it should be phi coming down from the z-axis. Yes, does this sound vaguely familiar? So my daughter had to do this problem last night. Does anybody know what is close to x squared plus y squared that would be nice to integrate on a sphere? So dv is going to be rho squared sine phi d rho d theta d phi. So if you want to do this in spherical coordinates, you would have the integral. I'm going to just write bounds because I don't really want to write them. Z is rho cosine phi, x is rho sine phi cosine theta, y is rho sine phi sine theta. Is this coming back to people? So x squared plus y squared is going to be rho squared sine squared phi. The cosine squared plus sine squared theta is going to reinforce to 1. And then you'll multiply by rho squared sine of phi d rho d theta d phi. And now you get to integrate sine cubed of phi. Anybody happy about integrating sine cubed phi? There's another way to do this. What is close to x squared plus y squared that you would love to integrate over a sphere?
X squared plus y squared plus z squared.
Right. So why don't we just add the plus z squared? Are you allowed to just add a z squared? What can you do if you want to just add a z squared? Subtract it. And so this would then become rho squared minus z squared. So the integral would be integrate over the bounds. And then you would have rho squared minus rho squared cosine squared phi, rho squared sine phi d rho d theta d phi. Is the rho squared sine phi integral? Yeah, the rho squared is not a problem to do. Is cosine squared phi sine phi an easy integral to do? Can you integrate cosine squared sine phi? So if you had to integrate cosine squared of phi, sine of phi d phi, phi goes from 0 to pi. What function has derivative cosine squared phi sine phi? Nobody remembers how to do this? So we want to integrate phi goes from 0 to pi, cosine squared phi, sine of phi d phi. It's not bad to use some of the time we have this semester to review things that you should have seen. What does this kind of look like? What would be a simpler version of this? If I You could, and if you did 1 minus sine squared, then you would have a sine cubed phi to do. And in fact, the way you actually do the sine cubed phi integral is you replace sine squared with 1 minus cosine squared, which is essentially what we're doing here. So baby is crying. We need to comfort this child. So you need to start giving me integration techniques. Name them.
Integration by parts.
Integration by parts. So you'd have to choose a u and a dv. What else do we have? U substitution. So what would be a good choice for u?
Cos theta.
Not theta,
Cos.
cos phi. So if u is cosine of phi, then du, derivative of cosine is minus sine of phi d phi. I like to remember, you have to remember, where does the minus sign go? The minus sign goes with the minus sign when you take derivatives. So this is almost nice. I mean, we just saw it by minus sign. So this is really just going to be minus the integral. Now, when phi equals 0, what does u equal? What's the cosine of 0? 1. And what is the cosine of pi? -1. So we just have minus the integral from 1 to -1 of u squared du. Right? I can use the minus sign to flip the order of integration. Oh, that looks so much better, going from -1 to 1. And now we just have u squared du, so that's u cubed over 3 at -1 and 1. And so it's going to just be 2/3. So it's important for these problems to think about, how should I attack them? If you don't remember how to integrate, start going through the list. Probably not partial fractions, as there's no fractions in play, right? It could be, could you do this with integration by parts? Could you do u equals dv equals? So I'll leave that as an exercise. Can you find a way to do this with integration by parts? The key thing here is I found it was easier to add z and subtract z. And that gave me, rho squared minus z squared. It makes things very nice. If you don't see that, when you have the sine cubed, you have to remember to write sine cubed as 1 minus cosine squared phi times cosine of phi. So the real challenge when you do these problems is figuring out how to use what you know. Quick question? Is question or anything? So you know all the different integration techniques, or at least you should, right? If you don't know them, who knows them? The computer, the web. And so it knows to just go through and try all of them. And when if you're trying to do this by integration by parts, it'll try u equals cosine phi, u equals sine phi, u equals cosine phi, sine phi, u equals cosine squared phi. Maybe it didn't try cosine squared phi, sine phi, and having dv be 1. It can try all these different things. When you're doing it by yourself, you have to figure out, what do I want to do? What do I want to choose for x? What do I want to choose for the group action? Do you remember your tests about when a sequence converges? So there's the ratio test and the root test. These are very mechanical. Take the ratio, take the limit. No creativity really required. Then there's the challenging one, the comparison test, where you show that it's always less term by term in absolute value than something that converges, so it converges. Well, what do you compare it to? That's where you have a little bit of an art. You have to figure out what to do. For these problems over here, the difficulty frequently is figuring out, what should you choose for x? What should you choose for the group action? Okay. I'm not going to go through the proof of corollary 6.26. I'm going to just paste it here. It's in the book. It basically goes through a very similar calculation. And it says if P is a prime and G is a group with P squared elements, then G is an abelian group. That's really nice because you might remember from a while back, we were trying to figure out what could the groups of size 9 be. And so if we take P equals 3, so the cardinality of G is 9, we could try to figure out what is it. So if there exists an element of order 9, then G is cyclic. So assume all x not equal to E have order what? So if an element has order 9, it has to be cyclic and we're done. If I take an element that's not the identity, what must its order be? Okay, but I told you it's not cyclic, so it must be 3. So we now know every element other than the identity has order 3. So I can start looking, and I know I have E, X, I have X squared, I have some element Y, I have Y squared. And now I have XY. And XY is the same as YX. Could XY be something already on the list? Could XY be one of these? So if it equaled E, then Y would have to be X squared. If it equaled X, so if XY equals E, that implies Y equals X inverse or X squared. And we're choosing something that's not X or X squared or E. So if XY equals E, that implies equals X. That implies Y equals E. If XY equals X squared, that implies Y equals X. If XY equals Y, that implies X is the identity. If XY equals Y squared, that implies X equals Y. So XY is a new element. So we have 1, 2, 3, 4, 5, 6. Yes, sir.
That's it.
And so I'll let you finish the calculation, but you can see now how much easier this is. And we can then start looking at what would be true about XY squared. Well, XY squared is going to be the same as X squared, Y squared. And so you can use this to try to get a sense of what the groups might look like. Okay, in the proof of the CELO theorem, so I think I've flashed the CELO theorems twice in previous lectures. One of the lemmas we need is that if P is a prime, N is some number greater than or equal to 0, M is greater than or equal to 1, and M is not divisible by P. So we're basically saying we're going to be looking at something of size P to the n M, and we're just factoring that number as some number of copies of P, n copies, and then something else M that is completely relatively prime to P. Then this number is not divisible by P. This should begin to look familiar to what we just did earlier today with the center, and maybe that's why I was spending so much time on this. This is a kind of contradiction we're getting, where one side is a multiple of P, so the other side has to be a multiple of P. And if we can get every factor but a couple multiples of P, then we know there have to be enough of those other factors to give us something that's a multiple of P. And so when we're looking at this, this is not going to be multiple P. So there's a couple of ways to do this. Any thoughts about how you could prove this? So it's got the brute force approach right here. And let's just multiply everything out. What's nice about binomial coefficients is you have a huge amount of cancellation. 110, choose 100. Well, almost all the factors cancel, and you just have 110, 109 all the way down to 101 over 10 times 9 times 8 all the way down to 1. Almost all the factors cancel. So when we multiply everything out, most of the factors cancel. And what they're saying is look at it term by term. So put the first two together, then put the next two together, then put, I should really do it in the order of the rainbow, et cetera, et cetera, et cetera. And just march down like that. And when you march down like that, we end up having these expressions over here. We know that our expression has to be an integer because we're counting the number of ways of doing something, right? There's not 2.37 ways of doing something. It has to be an integer. So all I have to do is show that it's not a multiple of p. I don't worry about if I have some denominators maybe that haven't been canceled yet. I know it's going to cancel at the end of the day because I know it has to be an integer. All I have to do is show that any multiple of p in the numerator occurs the same number of times in the denominator. And then that will mean that there's no p's left over. And the numerator can't be a multiple, and then the product can't be a multiple of p. So when I'm looking at this, we just need to show the power of p dividing p to the n m minus r is the same as for p to the n minus r. So we have to show that this is true no matter what m is. Are there any m that are easy to do? If I was feeling generous, what could I give you for m?
1.
1. So one possibility is let's just do it for m equals 1. Assume it holds for m up to a certain value, and then maybe try to do it for other m. By what method? Yeah, so try to do by induction. Does this fall by induction? So I'm not saying it does, I'm not saying it's not, but I'm saying it's a natural thing to try. M equals 1 is very easy because then you just have p to the n minus r divided by p to the n minus r. It's always going to be 1. So clearly it's never going to be multiple of p. And then just assume that you know it's true up to m and then show it's true for m plus 1. And if you can do that, then you're done. Okay, so that's one good way to do this. Another way is to say, we know p does not divide m. So we can write r as, p to the a times, let's say b. Where p does not divide b. And what can you tell me about a relative to n? How small could a be? So I'm writing r as some number of copies of p times a number that's relatively prime. How small could a be? What's the fewest multiples of p we could have?
0.
0. So we know a is at least 0, could A be as large as n?
Yes.
Well, if you look, what's the largest number we subtract? It's the last one. It's p to the n minus 1. R is strictly less than p to the n. So we know A has to be less than n. Right? So when we look at it like this, we know that A is at least 0, and it's strictly less than n. So if we look at p to the n m minus r over p to the n minus r, this is p to the n m minus p to the a b over p to the n minus p to the ab. What should we do to the numerator and denominator? So what should you do now? We want to show that whatever powers of p divide the numerator divides the denominator. So you've got lots of p's all over the place. What should we do?
Factor out the P.
Factor out the p. So what's the highest power of p I can pull out of the numerator? P to the a. So I'm going to get p to the a, and I can pull out a p to the a from the denominator, and then the numerator becomes p to the n minus a m minus b, and I'll get p to the n minus a minus b. So these cancel. Is the numerator a multiple of p? Remember, n is greater than a. So these two things are multiples of p as n minus a is greater than 0. And then we subtract something that's not a multiple of p. So the numerator and the denominator are not multiples of p. As b is not a multiple of p, not, I'll say, top and bottom are not a multiple of p. And so that proves that this expression is not going to be a multiple of p. So this was one of the key ingredients in one of the proofs of the Siena theorems. Okay. As a good exercise, try to prove this by induction. And maybe there's good ways to just group things. And if you know that it works for given m, well, what would happen if you had m plus 1? Okay. There was another item that was needed in the proof. So how might we create a subgroup of G having order p to the n? One way is to take a subset A having p to the n elements. Not every subset, however, will be a subgroup, right? It'll have the right size, it'll have p to the n elements, but it may not be a subgroup. So how can we tell if A is a subgroup? And so the book says there's a really nice equivalence. A is a subgroup if and only if, whenever you take any element little a in A, then little a times A is all of A. So because there's this equivalence, we have to go in two directions. One direction is probably not so bad. Which direction do you think is the easier direction? Assuming it's a subgroup and show the condition holds, or the condition holds implies it's a subgroup. 50-50 chance. Minimum. Could be better. They might both be equally good. Would you rather assume it's a subgroup and show that the condition holds, or show the condition holds and that implies it's a subgroup?
close to imply the subgroup.
All right, so you want to do that direction? You sure?
It's a 50-50.
It's a 50-50 chance.
I'm just curious, I don't get how little a times a equals a is a subgroup.
Well, that's what I have to prove.
Oh,
So you shouldn't be getting it. Yes. Yep. So it's, which do we think is easier? Showing that that condition implies it's a subgroup, or showing that it's a subgroup implies the condition?
Subgroup implies it's a condition.
I think it's going to be easier to show the subgroup implies the condition, because when we know it's a subgroup, we have a lot at our disposal that it's a subgroup. So I would say, let's try doing this direction first. And again, they might be equally good. Our intuition might be wrong. So because it's a subgroup, we now want to show that for any A in A, okay, well, so consider A must show it equals A. So how do you show it equals A? That means given anything in A, it has to be here. I'm sorry? Okay, so choose an X in A, must find an X tilde such that A X tilde equals X. Any thoughts on what X tilde would work? X tilde has to be in A. So you are right that closure is going to help us. What should we take X tilde to be? So we need to multiply something by A and get X. What should we take X tilde to be? Solve the equation.
A inverse X.
A inverse X. And that is an A by closure. Then A X tilde would be A times A inverse X, which is A inverse by associativity X, which is EX, which is X. So this shows that we can get everything. So you give me anything in A, and it's in little a times A. Have we shown that the two sets are equal? So this shows A is contained in A little a times A. Right? We just showed you give me anything in capital A, and I can write it as little a times something in big A. But that's not the same as showing that they're equal. If they were finite sets, they have the same cardinality, we would be done. But if they're infinite sets, we wouldn't be done. But there's a suggestion to use closure. Because A is a subgroup, where does little a live? It lives in G, but it lives in something even smaller than G because it's a subgroup. By closure, where does little a big A live? It lives in A, right? By closure. So we're done. So you have to be really careful about this on exams. You have to be really careful about this on the homework. It's not enough to just show that A is contained in little a big A. You have to show either the other direction, that little a big A contains A, or just show that it's contained in, anyways. So we just have to be a little bit careful. Okay, so that's one direction. Now we have to do the other direction. Assume for all A in A, AA equals A, prove A is a subgroup. Okay. So we are now doing the other direction. We're assuming that this condition holds. So no matter what element little a you take, so which properties do we have to prove? Closure, associativity, inverse. What's the last one? Identity. What's the easiest one to do? Nope. Associativity, right? Why is associativity the easiest? It's inherited. So associativity, inherited. All right, now let's do closure. So let's say A1 and A2 are in A, is A1, A2 in A. So we must show A1, A2 of A equals A. Does everyone agree that that's what we have to show that it's closed? But A1, A2 acting on A by associativity is the same as A1, A2A. What's A2A? A. Why?
For all A.
Because we're assuming that this holds for all A and this is an A where it holds. So this is just going to be A1A. Oh, but what is A1A? A. So it's closed. Now we have to do inverses. So if A is an A, show A inverse is an A. But A and A means AA equals big A. Little a big A equals big A. Any Dr. Seuss fans? There was one book with, big A, little a. What's this one? Not as popular as Cat in the Hat. What should we do to both sides?
Left multiply by A.
Yeah, so multiply on left by A inverse. And so we get A inverse A big A equals A inverse big A, or the identity A equals A inverse A, or A equals A inverse A. And we now have inverses. So what's the only thing that's left? So what's the only property we still have to do? Identity. So we must show that the identity is an A. If not, we have AA equals A. So there has to exist some X in A with A times X equals A as, no, I'll do it direct. I'll do it as a direct proof, not as a proof by contradiction. We must show the identity is an A. So if little a is an A, since little a big A equals A, then there exists an X in A such that A times X equals A. Because we know little a is in big A, and we know little a big A is also big A, So there's got to be something I can multiply little a on the right by and get back little a. Well, what does that tell you x has to equal? So if little a x equals little a, what does it tell you x equals? Therefore, x has to be the identity, so E is an A. So this proves that this is an equivalent. These two conditions are equivalent. If I want to show something as a subgroup, I can either go through and check all the conditions. Is it closed? Does it have inverses? Is it associative? Is there an identity? Or I can just show for any little a in big A, little a big A equals big A. It's a matter of which one you want to do. Yes.
Does this rely on G having PDN elements, or could we generalize?
So nowhere, good question, nowhere in this proof did we use that it had P to the n elements. So in the proof of the Silo theorem, we needed to create a subgroup of G having order P to the n. And so the book used this result. But this result is actually true in general, and nowhere in this proof are we using that we have size P to the n. I will risk another multivariable calculus question. Do people remember that there's such a thing as a directional derivative? You can calculate it with the definition of the derivative and the limit, or you can just say it's the gradient dotted with the vector. And once you know that it's the gradient dotted with the vector, you will never calculate it in any other way. Or if you remember your stats, there's two ways to calculate the variance. It's the expected value of the square of x minus the mean, or it's the expected value of x squared minus the square of the mean. Both of those give you the same. Which one is easier to work with? It depends on how things are presented. That's what's going on over here. Is sometimes when you have various things like this, sometimes one is more easier to use than another. Hopefully you've seen this phrase sometime in your math career, TFAE. The following are equivalent. They give you a whole list of things that are equivalent. And typically it's 1 implies 2 implies 3 implies 4 implies 1. You have some kind of circular argument like this. And once you have that, once you have one condition, you then have all the others. And it's just which is going to be the easiest one to use. Okay, so now we come to the Silo theorem. So we have theorem 6.29. If we have a finite group G, P is a prime, and P to the n is the highest power of P that divides the size of G, then G has a subgroup of order P to the n. So if G is of size 12, there must be a subgroup of size 4. There must be a subgroup of size 3. Does there have to be a subgroup of size 2? We don't know from this. So the book answers that question. Right now, we do not know the answer to that. It answers it very shortly after 629. Right, if you skim down a little bit on the slide, you see remark 6.32 that says, yeah, it doesn't have to be the highest power. You can find ways to get something that will work. So definition 631, if G is a finite group, P is a prime, and P to the n is the largest power of P that divides the size of G. We say a subgroup of size P to the n is a P-Silo subgroup. Okay, we know that such a group exists by theorem 629. I am not saying anything about which prime. I'm not saying that this is the largest prime that divides the size of the group. I'm not saying it's the smallest prime. I'm just saying any prime. You give me any prime that divides the group. You look at the highest power of that prime that divides the size of the group. There will be a subgroup of that size. The next part of Silo's theorem, theorem 635, is it actually quantifies just how many there are. I'm not going to go through this in detail. I think you have one homework problem where I want you to make sure that you can use something like this. I will not be putting a Silo theorem on the exam. Okay. I will have it as a homework problem. I want you to be able to just do one calculation like this. But the really useful part is part C, which gives you some idea of how many CELO subgroups can you have. And by playing certain games like this, you can frequently use it to figure out just how many possibilities there are for the group. And if you're really lucky, there'll only be one possibility. Or maybe two. We saw for some small primes like 2, if I gave you a group of size 4, there were only two possibilities: a cyclic group of order 4, or a group 1 x, y, z, where x squared equals y squared equals z squared, and then there was some rules about what is x times y in terms of z. So there's a lot that you can do about this. There's an entire industry about trying to classify which finite groups are possible. And one of my professors at Yale, Professor Feit, was one of the two people who finished the classification. This is the beautiful Feit-Thompson theorem. Depending on how many papers you include in the classification of these finite groups, it's easily over 1,000 pages of all the different possibilities. Most things are very nice, but then there's some really strange examples that arise. And there's a lot of powerful techniques to do these analyses. So I am not going to go through the details of the proof. The hardest part is going to be, we want to find a p-CELO subgroup. We're trying to show that something exists. So we're looking for a set with p to the n elements. And so, anybody have any idea what formula we're going to use? What do you think, given what we've been using in this chapter, what do you think we're going to be using? This is the Chekhov gun method of mathematics. The orbit stabilizer theorem. So we're going to somehow use that the size of x is equal to the sum, I goes from 1 to k, of the size of g divided by the size of the stabilizer of xi. And what we have to do is, what is x? And how does g act on x? And so what we will do, I believe, is x is these all subsets of size p to the n. And I believe it's left multiplication. So this is an example where it's not acting on itself. This is a reasonable thing to have it act on. I'm trying to find a subset of size p to the n that's a subgroup. Let's look at all subsets of size p to the n, and hopefully one of them will have the desired property. Hopefully this also gives you a sense of why we proved this equivalence. This will be a way of telling, if we multiply by something, I said right multiplication. I mixed up my right and my left. That when we multiply on the left by little a, we get back what we started with. So really over here, let's change this to right multiplication. Oh, no, I wrote left multiplication. Did I say left or did I say right? I did say left, okay. It's nice that I can always check. One of my colleagues has the incredible skill of being able to speak in one language and write in another. And so I heard him give, talks in English and write in French and vice versa. Okay, so hopefully this gives you a sense of why we wanted this result, where this is going to come into play. I'm going to be looking at all subsets of size p to the n, and this is going to help me identify which one I want. But again, the challenge in all of these is determining when we can have a good choice of X and a good choice of group action. So sadly, you need two key ideas. What is X and how is G going to act on X? Okay, I want to just spend a little bit of time today going over a few things that you should have seen, but maybe have not seen. Has everybody seen the exponential function? Okay. And so if I give you e to the x times e to the y, what does that equal? Everybody agree that it's e to the x plus y? Why is e to the x times e to the y e to the x plus y? I saw you. Yes? Just is. All right, and you're moving both hands, so it's got to be true. All right. Yeah, when you go like this, that's only one hand. Come on. Did I give you guys what's the derivative of x squared, x to the 3/2? Did we do that? Did we do that this semester? Okay. So derivative of x squared, what is that? Please don't make me find and hunt down your calculus teachers. Derivative of x squared. 2x, thank you. Derivative of x to the 3/2.
3/2 x to the 1/2.
Okay, derivative of x to the root 2. Excellent. So you got them all right. But now I want to see your logic. So we take the limit as h goes to 0 of f of x plus h minus f of x over h. I should have done these all in different colors. So for this one, x plus h squared, can we expand what x plus h squared is? Yeah. How do we do that? Right, but what allows us to do this? I'm sorry? Binomial theorem, excellent. So this is the binomial theorem. I can do x plus h to the n for any n. What about x plus h to the 3/2? We don't have the binomial theorem there. There are two ways to do this. One, and hopefully this will impress you, is this is x plus h to the 3/2 minus x to the 3/2 over h, right? I can multiply by 1 without changing anything. What's a good choice of 1 here?
X plus h 3/2 plus.
Excellent. This will then look like the limit as h goes to 0 of x plus h cubed minus x cubed over h times 1 over x plus h to the 3/2 plus x to the 3/2. This part over here, sorry, green, the green never shows up well. So this part over here, that's going to go to 1 over 2x to the 3/2. And this part over here is going to go to 3x squared. And when you combine them, it's going to work. So that's one way to do that. The other way to do this problem for x to the 3/2 prime could also do if f of x is x to the 3/2, let's let g of x be f of x squared is x cubed. So g prime of x is 2 f of x, f prime of x is 3x squared. Thus, f prime of x is 3/2 x squared over f of x is 3/2 x squared over x to the 3/2 is 3/2 x to the 1/2. So if you thought you knew the derivative of x to the 3/2, have you seen either one of these two arguments? Or did your teacher slip this past you? It's really easy to slip things past. I know some of you are considering being teachers. This does not mean that you have to do this in a first calculus class. But it does mean you have to emphasize to students, when we do the rule, the derivative of x to the r is rx to the r minus 1. We proved it when r was a positive integer. We can extend it to a negative integer with some work here. We have ways to do it when it's a rational number. What the hell does x to the root 2 even mean? You all got it correct. Way to go. And you have just demonstrated that you can formally manipulate mathematics. Wonderful. But what are you manipulating? What does x to the root 2 mean? What does it mean to take a number to the root 2th power? You all did it well. This is the danger. We know how to work with integers. This is the same as x to the root 2, as e to the root 2 natural log of x, which is in the sum and goes from 0 to infinity of root 2 natural log of x to the n over n factorial. That makes sense. And so the only way we can understand something like x to the root 2 is to actually put it into this infinite sum. And now we can work with it if we understand the exponential function. But you've got to be really careful. So over here, when you said e to the x, e to the y is e to the x plus y, technically what you have is you have the sum, n goes from 0 to infinity of x to the n over n factorial, times the sum m goes from 0 to infinity of y to the m over m factorial. Does that equal the sum, let's say k goes from 0 to infinity of x plus y to the k over k factorial? If the answer is no, then the math notation sucks. There's no gentle way around it. It would be terrible notation to denote this as e to the x, because you want to basically use exponent laws. What's 1 over cosine?
Sine.
No, 1 over cosine. One secant.
Secant.
And what's 1 over sine? There is a reason why cosine goes with secant and sine goes with cosecant. It has to do with it. When you first hear, it's like, why are they doing this to me? It could just be really bad notation. You have to prove this. So the way you would prove this very carefully is this is the same as the sum. K goes from 0 to infinity. The sum, L goes from 0 to k of x to the k minus L, y to the L over k minus L factorial, L factorial. Is when again, I'm not going to justify, but everything converges so quickly because of the factorials, I can do whatever I want. I can rearrange the terms, I can make this rigorous. And what I'm just saying is, when I multiply things together, I have some powers of x and some powers of y. So they have to sum to some number. Let's put all of the x and y's that sum to 0 together. All the x's and y's whose powers sum to 1 together. All the x's and y's whose powers sum to 2 together. And that's what k going from 0 to infinity means. Now, hopefully, when you look at this, you see a k minus L factorial, L factorial. Something should be going off in your mind. This should look like something. Combinations, what are we missing? what are we missing? What would we love to have? You've got a k minus l factorial and an l factorial. Yeah, you'd love to have a k factorial. So can we just put a k factorial upstairs? So as long as we divide by k factorial. So this would then be the sum, k goes from 0 to infinity. I can pull the k factorial in the denominator out. I have a sum, L goes from 0 to infinity, and I'm going to have k choose L x to the k minus L y to the L. But this is just x plus y to the k. And that's the proof. So as long as you can justify moving things around, e to the x times e to the y is e to the x plus y. What kind of quantities are x and y? These are real numbers, complex numbers, something nice like that. You should hopefully know e to the ix is cosine x plus I sine x. You can get this from Taylor series expansions. Have people seen this before?
Yes.
All right. I'm going to show you now how to get basically every trig identity immediately. Okay, what's e to the ix times e to the minus ix?
E to the 0. So
E to the 0, which is
1.
But this is cosine x plus I sine x, cosine x minus I sine x. And so just e to the minus ix is cosine negative x plus I sine negative x. But cosine's an even function, so it's just cosine x. Sine is an odd function, so it's minus sine of x. Well, when I multiply this out, I'm going to get cosine squared x, I sine x cosine x minus I sine, those cancel, and then I have a minus I squared. What's minus I squared?
1.
1. So I get cosine squared x plus sine squared x equals 1. There's Pythagoras. What's e to the ix times e to the iy? E to the ix plus y. So this is going to be cosine x plus I sine x times cosine y plus I sine y is cosine x plus y plus I sine x plus y. So if I multiply everything out, the real part on the left has to equal the real part on the right. The imaginary on the left has to equal the imaginary on the right. So I'm going to get cosine x cosine y minus sine x sine y is cosine of x plus y. And I'll get sine x cosine y plus cosine x sine y is sine of x plus y. You can basically get every trig identity you need once you remember the exponential function. And this hopefully gives you an understanding of why you have some of these trig identities. So whenever you hear the word associative, what word do you associate with that? Inherited. The trig functions are inheriting this from the exponential function. The exponential function is a map between different sets of numbers. I have maps between different functions. And so we were talking about group homomorphisms and whatnot. There's a much deeper connection that I can go into. I'm just trying to give you the tip of the iceberg in terms of these homomorphisms and these mappings passing from one thing to another. We are basically passing from exponential properties to trig properties. And so I'm not going to go into too much detail as to why you might hear about multiplying e to the x times e to the y, where x, y are matrices. But it turns out, has anybody here taken differential equations? All right, so have you used matrices and matrix exponentials to solve differential equations? Oh, I don't remember. So it turns out we have e to the x is the sum, n goes from 0 to infinity of x to the n over n factorial if x is a complex number. If I put in a matrix, anybody want to guess how you would define e to a matrix? We've got the definition of e to a number. How would you define e to a matrix? So, okay, if you define, yeah.
Each entry like raised to each entry.
So, say that again.
Raise each entry of the matrix.
So what you would then do is you would have a new matrix where the 1 by 1 entry would be e to the a11. The 1 2 entry would be e to the a12.
What are you asking?
I'm asking you.
Yeah, something like.
So that's one way to do it, right? And you could, and there's often more than one way to do things. And you can just say, we're going to do it point-wise. And if you're looking at a lot of computer programs, they actually do have stuff like that, where they would apply this point-wise. How else could you do this? You have the formula for e to the x. When x is a complex number, what could we do?
Do the same thing, but replace x with x.
Yeah, are there any conditions we need on A if we want to do this, for this to make sense? What kind of matrix does it have to be if we want to have A times A make sense?
Square.
It has to be a square matrix. So it turns out that this actually works, and this gives you a definition of E to a matrix. This is very useful in solving differential equations. It's very useful in physics. The reason I want to do this is I wanted to state one of the more interesting formulas in mathematics, the Baker-Campbell-Hausdorff formula. And it allows you to calculate z when you have x and y. So if I do e to the x times e to the y equals e to the z, if life was nice, z should just be x plus y. But what's different between matrices and numbers? What property typically fails for matrices?
Commutativity.
Commutativity. And so this measures the failure of commutativity. And so here, xy is xy minus yx. If x and y commuted, what would xy minus yx equal? 0. So this is a measure of the failure for x and y to commute. If they commute, then e to the x, e to the y is e to the x plus y. So all the stuff we're doing in group theory, here's some interesting applications of stuff like this. Here's some interesting applications of you're trying to see which things commute and whatnot. There's lots of other ways of writing these formulas and whatnot. There's whole theories behind stuff like this. We're not going to go into details of this. I just want you to see that the stuff that we're doing does have applications. All right, so I'm going to just stop here now.